Now in this slide, we have sine functions at different amplitudes. And so starting with the right graph, we have three of the graphs, or three of the waves we're going to go over, along with the traditional y equals sine x. So that red wave there can serve as a reference point to compare the graphs we're going to go over visually. And so starting with the graph in the upper left-hand corner, we have y equals negative sine x. And one thing I noticed about y equals negative sine x in comparison to y equals sine x is that it reverses the maximum and the minimums of y equals sine x. So referring back to the other slide, the patterns here are reversed. So from origin to rightward, we have intercept at 0, minimum, intercept, maximum, intercept. And then going origin to leftward, we have intercept at 0, maximum, intercept, minimum, and then another intercept. And so visually, that's kind of how it differs from y equals sine x. Okay, so below that, let's move on to y equals half sine x. If we multiply the standard range of y equals sine x, which is -1 for its minimum value and 1 for its maximum value, by 1/2, we get -1/2 at its minimum and 1/2 as its maximum. Thus, we halved the standard minimum and maximum from the midpoint. And so visually, when you look, y equals sine x has a much taller peak and a much lower depth than y equals 1/2 of sine x. And so that's kind of how they compare there. And then lastly, when we look at y equals 2 times sine x, which is the graph right next to y equals negative sine x, if we multiply the standard range of y equals sine x, which is again -1 for minimum and 1 for maximum by 2, we get -2 for minimum and 2 for maximum. Thus, in y equals 2 times sine x, we doubled the standard minimum and maximum from the midpoint. And when we compare visually, the height and the depth are much more extreme than y equals sine x. And so those are kind of how they compare visually. And again, this slide on the right shows all of them together, which kind of gives a better picture of how those differences look. Here we have sine functions at different frequencies. And if you look on the right, we have both sine waves that I'm going to go over along with their traditional y equals sine x in red. And so that can again kind of serve as a reference point as I go through the other sine waves. And so starting in the upper left corner with y equals sine of 2x, I noticed that the frequency factor is 2, meaning the cycles are twice as frequent as y equals sine x. Now, since the distance required for y equals sine x to finish a cycle is 2 pi, and y equals sine of 2x gets doubly as much done in the same distance, or is doubly as frequent, it's only going to take a distance of pi to complete a cycle. Therefore, when I look at it, y equals sine of 2x is a lot more condensed in the same distance than y equals sine of x. And so that's how those compare visually. Below that, I have y equals sine of 1/2 of x. And this is kind of on the opposite hand. This means the cycles are half as frequent as y equals sine x. And so since the distance required for y equals sine x to finish a cycle is 2 pi, and y equals sine of 1/2 of x gets half as much done in the same distance, it's going to take a distance of 4 pi to complete a cycle. And that's why when I look at this one, I see a lot less waves than y equals sine x in the same distance. And the wave is a lot more stretched out because it takes a lot longer to catch up with y equals sine x. And so that's kind of how they compare visually. And if we look again in this third graph on the right, you get to see all those waves and the differences together. Similarly to sine functions at different amplitudes, I'm going to go over cosine functions at different amplitudes. And so if we look on our right, we see both cosine waves that I'm going to go over along with y equals cosine x in purple. And so starting in the upper left-hand corner, we have y equals 3 times cosine x. Now, looking at this, we notice that 3 is in the place of the amplitude. And so if we multiply the standard range of y equals cosine x, which is -1 minimum for its y value and 1 maximum for its y value by 3, we get a range of -3 minimum and 3 maximum. Therefore, we tripled the standard maximum and minimum distances from the midpoint. And so comparing these, the height and depth of y equals 3 times cosine x is a lot more pronounced than y equals cosine of x. And so those are how those two are going to appear differently on graphs. Now below that, we have y equals -1/4 cosine x. Now, again, if we multiply the standard range of y equals cosine x, which is -1 at its minimum and 1 at its maximum, by 1/4, we get a new range of -1/4 at its minimum and 1/4 at its maximum. However, because we have this negative sign in front of 1/4, it's not just 1/4 times the range, it's -1 times 1/4 times cosine of x. So now, if we multiply those minimum and maximum values by -1, we're going to switch the placement of the minimum and maximum points on the graph, just like how we saw negative sine x switch the maximum and minimum, the maximum and minimums compared to y equals sine x. And so, looking at that pattern, if we go from the origin to rightward, we have the pattern of minimum, then intercept, then maximum, then intercept, then minimum. And then looking from the origin to leftward, we have minimum at 0, then intercept, then maximum, then intercept, then minimum. And so not only are the waves much less pronounced compared to y equals cosine x, but the minimum and maximums are also reversed. And so if we look at, again, this picture of all three graphed on the coordinate plane, we can see the differences a lot more clearly between all three. Okay, wrapping up, we have cosine functions at different frequencies. So, as always, we have two of the cosine waves I'm going to go over, and then y equals cosine x in the middle. And so, starting with y equals cosine 4x, again, in the upper left-hand corner, we notice that 4 is our frequency factor. And this means that the cycles are 4 times as frequent as y equals cosine of x. And so since the distance required for y equals cosine of x to finish a cycle is 2 pi, and y equals cosine 4x gets 4 times as much done in the same distance, or is 4 times as more frequent, it will take a distance of pi over 2 to complete a cycle, or it's going to take, 1/4 the distance that y equals cosine of x is going to take to complete a cycle. And so, therefore, if we look at that, we notice that y equals cosine of 4x is a lot more condensed in the same distance than y equals cosine of x. And so those are how those two differ visually. Now, if we look at y equals cosine 1/3 of x, we have a similar but opposite problem. This means the cycles are as frequent as 1/3 of y equals cosine x, so it's less frequent. And so since the distance required for y equals cosine x to finish the cycle is 2 pi, and y equals cosine of 1/3 gets 1/3 as much done in the same distance, or is 1/3 as frequent, it will take a distance of 6 pi to complete a cycle. And so if we compare, we see that y equals cosine 1/3 of x is a lot more stretched out and takes a lot longer to complete its cycle than y equals cosine of x. And so looking at all of them together, we can see how each of those compare not just with y equals cosine of x, but with each other. And we can notice that y equals cosine of x is kind of the middle ground between the two extremes of frequency. Finally, for my last slide, I wanted to go over my sources. And so the first source is just contributing to the history of the coordinate plane. The second source is about additive synthesis. And the third source is about how engineers use sine waves. And then fourth source is about, again, goes into the history, specifically about the inventor and the I think therefore I am. And then the fifth source is about the history as well with the coordinate plane. And so I just wanted to give a quick explanation of what those were.